Message that we're recording. All right. Great. Okay. Well, we're very happy in our kickoff meeting today to have two speakers. Grant Meyer is going to go first, then we'll hear from Jason Briner. Grant has held faculty positions at Middlebury College and the University of Oregon and is now an emeritus professor in Earth and Planetary Sciences at University of New Mexico. He retired back in 2021. He earned a BS in geology from the University of Idaho in 1978, a master's from Montana State in 86, and a PhD at UNM in 93. His primary research and teaching interests are in hill slope and fluvial geomorphology across the West, and his work on geomorphic response to modern and Holocene wildfires and their relation to climate in Yellowstone was recognized by the GSA Kirk Bryan Award in 1997. Over about 25 years, he ran projects on equilibrium line altitude reconstruction in geomorphology courses, and that's what we're going to be hearing about today. So take it away, Grant.
Thank you very much, Ben. And so everybody's seeing my intro slide here, right? Um, Hello?
Yep, you're good.
Okay, very good. I'm sure that some people out there will recognize a view that's similar to what Ben already showed, i.e. the east front of the Sawtooth Range in Idaho, with Yellow Belly and Pettit Moraine Dam lakes here. And I in part show this because glaciers, paleoglaciers of the size of Yellow Belly here, we didn't work with much for reasons to be explained. More like, see this range front cirque here and its associated very small valley glacier. Um, but first of all, um, I thought it might be appropriate to have a brief moment of silence for all the glaciers that have passed away in the last year. And that would not exactly include this one in Switzerland, which actually was declared dead in 2019 and a funeral was held. So, um, moving to hopefully more entertaining or less depressing stories. First, I want to acknowledge the people who taught me what I know, which is not a great deal. Again, I'm humbled to be in the midst of a lot of paleoglacier experts here, which I am not. But what I know, I learned a lot from Bill Locke at Montana State. And of course, he was basically the inspiration for work on equilibrium line altitudes. Ken Pierce was on my PhD committee. I think here he's describing a grizzly bear encounter in Yellowstone. And then there's some goofy looking guy behind him, looks a bit like a younger version of myself. But again, this work was conducted largely in the context of geomorphology lab projects. I later refined much of the mapping and tried to do quality control. But of course, also instrumental in the work were TAs for the course, which include Jen Pierce, former PhD student, also Lyman Persico, who are both in their respective faculty positions now running their geomorph labs on their own. And again, since um, let's see, was there a question or okay? I just heard a little bit of voice, but yeah, many University of New Mexico geomorph courses in particular contributed here. Here's one out in the Sandia Mountain front, unglaciated. So one of the reasons that back when in the early 1990s I started these projects in the classes, just first of all, just very basically wanting to have a more detailed or more accurate representation of elevational controls on and others on glaciation in the West, but was definitely inspired by and impressed by the work of Steve Porter and Ken Pierce, Tom Hamilton in their compilation in 1983. And here their contours are on cirque floor elevations, which, again, I would hope that our work on provides a more accurate indicator of the climatic environment in which glaciers have occurred. And also, at that time, it wasn't too much after the work by CliMap and CoMap on modeling circulation patterns associated with the big ice sheets to the north and comparing those to paleoclimatic data, largely pollen, with some reasonable agreements. The easterly flow at the south end of the big anticyclone over the Laurentide and Cordilleran ice would presumably result in colder and drier uh, climate in the Pacific Northwest, which seems to be borne out by the paleoclimate data. Late in the glaciation, you actually see the still persistent uh, anticyclone by this model, but with the jet stream having moved farther north. And of course, there's been work by folks, including Glenn Thackeray, suggesting that that resulted in later phases in the last glaciation promoted by increased precipitation. So, yeah, what might the ELAs tell us about uh, these kind of climatic controls? Um, so, in terms of how we conducted the work, initially it was on, well, basically it's all been on USGS topo maps, at times aided by Google Earth, and uh, not really, but just very lately with LiDAR imagery. And again, we initially with paper maps and planimeters, pretty time consuming, then terrain navigator, topo map software. But in recent years, it's been really nice to be able to use free caltopo.com uh, topo maps, which allow you to draw polygons, measure areas very easily. And so, of course, we're looking for diagnostic glacial features to um, map last glacial moraines. I should note that, of course, in a lot of cases, especially with the smallest glaciers, it's hard to distinguish, hard to tell whether you're looking at last glacial moraines or maybe some from, well, let's just say Bull Lake, to use that term, or some pre-isotope stage 2 glaciation. But, we're looking for sharp-crested lateral moraines in particular, where we can see them, trim lines. But of course, there's a lot of approximation involved in this mapping. And then we're applying the simple assumption that the in the AAR method, accumulation area ratio, that the ablation area is 0.35 times the total area. And that we'll just use that simplification for all of our small glaciers. Aspect, which we'll talk quite a bit about, was just simply estimated by eyeball. It seems to work fairly consistently. You get repeatable results just by eyeballing a line down what's a relatively linear glacier like this one, giving an aspect of 55 degrees. Of course, there are larger and more complicated glaciers in which that measure of aspect is going to be misleading. And of course, these days one can calculate insolation over the whole surface of the glacier, not something that we had time for in geomorph glass labs. But again, because it allowed us to really reduce the amount of error and make mapping much easier for what are really beginning geomorphology students. We focused on small glaciers, cirque glaciers, valley glaciers, and those less than 10 square kilometers are 97% of the full data set. Um, but of course, also these smaller glaciers tend to be more subject to things like shading, topographic shading, controls on insulation, wind loading over ridges, which I will suggest later is a pretty substantial factor in the overall patterns that we see. Um, so ultimately, uh, these yellow crosses are the data locations for the full data set over something like 25 years, but also including Eric Leonard's data, which he's very graciously shared for the San Juan Mountains, very dense there. Bill Locke's data for Western Montana. I'm going to use this somewhat obnoxious laser pointer. Jeff Monroe and colleagues' data from the Uintas, and then published data by Zielinski and McCory for Nevada. And I have a few of our own estimates mixed in those areas as well, but just a few. And here again, you can see a histogram of the size of reconstructed glaciers, the large majority of them even less than 5 square kilometers. And again, acknowledgement to Eric for both his generosity and his insights in doing this project. So one of the things that I really liked early on was the fact that central Idaho just has a huge number of small glaciers continuously across that landscape. And so it's a good place for looking at spatial patterns in the ELAs. But a little bit more about reconstructions here. Here's some examples from the east front of the Sangre de Cristos in New Mexico. And you can see that in this case, for example, at least on the lower ablation area, we have nice sharp crested lateral moraines. Pretty good for this Enchanted Lake Glacier here as well, and what seemed to be pretty clearly a terminal zone there. Little less obvious here in the old Rito Morphe. And, you know, one of the uncertainties is you have a sharp crested bedrock ridge, which is what I think this is. It's kind of out of scale for a lateral moraine. But again, being restricted to topo maps and not field checking any of these, well, I shouldn't say any, but very few of these estimates. I'll also say at this point, very few of them have been checked with basal shear stress estimates to see if we got ice thickness somewhere right around the equilibrium line. So there's certainly sources of error here. But let's see here. These days, oh, sorry, I'm getting ahead. Here's an example of a smaller glacier, about a quarter of a square kilometer, where, and we run into this fairly often with the smallest glaciers on topo maps. They're just not any real obvious lateral moraines. Maybe this is some reflection of that. We see the valley here or gully get narrower and steeper, so it doesn't look so much ice scoured. And I think our ELA here is probably not too far off from what you'd get if you did this little cirque and the Middle Fork Lake cirque here too. But again, plus or minus 50 to 100 meters in most cases, I think is probably realistic. So again, of course, these days we have these beautiful LiDAR images to use, which we're not able to use in the geomorph class up to 2021. But in any case, I think we did pretty good with the northern two of these glaciers. If you just compare the overall shapes, not so much with the rhedomorphy. The terminus is about in here on the map on the left, but if we go ahead and map it in light of the LIDAR, which what I'm seeing is lateral down to terminal moraine zone there. Um, we get a ELA that's lower than about 54 meters from the previous um, estimate. One thing I might just note as a detail in this part of the world, these ELAs on the east front of the Sangres in New Mexico are relatively low compared to other parts of that range and in the broader neighborhood. And talking to our UNM climatologist, Dave Gutzler, he made it says, oh, it's the upslope. It's those spring storms, as in the Colorado Front Range, that can dump a whole lot of snow late in the season. I think that might be involved, but I also, in these cases, there's this big plateau-like surface along much of this part of the Sangres where there's a very good opportunity for wind transport of windblown snow to get dumped over the ridge here and into these valleys. So another possibility for those low ELAs. Okay, so let's see here. I seem to have frozen for some reason. I don't know. Come on. Uh, I
Grant,
hope I
you
don't.
seem to be good on my end. Hopefully it's
I don't need to report here. Oh boy. Not sure why that happened. It's always something. Okay, I have to reopen. So what happens with retired guys that limp along with old computers, I guess. Uh, there we go. The slides actually come up.
Hey, Ben and Grant, would this be a good time for me to chime in here for a moment?
I'm ready to go again. Hopefully
Okay, never mind.
Okay. Moving ahead, and I'll uh, speed this up. So ultimately, contouring all the paleo ELA data, including that from Eric Leonard, et cetera. We
Grant,
get,
sorry to interrupt, but I don't think we can see your slides.
uh-oh. Okay. Let me go back. Did I get booted out of the meeting? Okay. How's that look?
Yep, you're back.
Okay, very good. All right. In any case, the contours, and these are very smooth, of course, are broadly similar to what you can see in the old Porter-Pierce Hamilton cirque floors. You see things like Eric's already published high and dry core of the San Juans. We see a similar kind of effect here in the Abserica Mountains east of the Tetons and northern Wind Rivers. So there's pretty good evidence for westerly flow and some topographic orographic effects and rain shadow effect, basically, or snow shadow. So because of that continuous data across central Idaho, that's been an area of focus. And of course, we've got a relatively wet area on the west end, the driest parts of Idaho over here on the east side. So a strong contrast here in snow water equivalent. And if we simply take this transect box and plot the ELAs there, we get a very strong relationship with longitude, just simply showing higher ELAs to the east. And of course, consistent with snow precipitation control on ELAs. Okay, of course, back in the previous map, there's obviously a low north, high south pattern in the ELAs as well, but it's these east-west ones that are kind of interesting. One detail here, again, sort of rain shadow effect. Seven Devils Mountains are right here, lying directly east of the higher Wallowa Mountains in Oregon, and they have these kind of anomalously high ELAs. If we separate out these data by aspect groups, what you see just generally is that the southeast through west facing aspects tend to plot above the regression line, again, suggesting, well, in this case, greater insulation, especially late in the day for southwest and west. So greater ablation potential there. And going off of that regression, if you take the residuals by aspect group from that regression line, you see that the north through east are either close to the regression line or below for the north, showing lower ELAs, as you might expect, but then much higher ELAs in the southeast through west aspects, except for the southwest. But keep in mind that all these aspects have limited numbers of data in the southwest in particular. It's only one data point. So within this Idaho transect. So yeah, pretty good indication of insulation control. And that is borne out by just looking at the numbers of glaciers and the different aspects, and here plotted by azimuth. Very few in the southeast, up to the west, northwest, facing directions. Okay? And I will say that we tried so that we could test this. Now, this isn't some fancy random sampling scheme, but we simply tried to get all the aspects that were represented. And it's just, of course, hard to find those hotter sun-facing paleoglaciers. So again, thinking about these broad-scale climate controls, back in 2004, I worked with Peter Fawcett, and he did some general circulation modeling of the LGM, and we're looking at the Idaho study area in this little red box here. And what we see is certainly an anticyclonal pattern, but it's pretty small and weak compared to the classic older studies showing centered over the Laurentide and very large scale. Of course, there's a Greenland anticyclone here. But keep in mind, these are surface winds on the left. But if you look at the 866 millibar winds, they're near the top of the boundary layer, but still within the flow that can be carrying a lot of moisture, and they show pretty strong flow across the Idaho area from west east. And I think this is consistent with what, for example, Joe Liccardi and Ken Pierce have noted about LGM glaciers in the Rocky Mountains, that they don't seem to be too much affected by the old anticyclone easterlies. And if we go to a little later time, 15 Ka, it's not terribly different in terms of the pattern. still some disruption of the westerly flow at the surface winds, but stronger flow uh, uh, higher up at the near the top of the boundary layer. And then present day, just for comparison with our prevailing westerlies, obviously showing up over the middle and northern Rockies, and very strong westerly flow at 866 millibars. So I think those things are generally consistent with what we see in the ELAs. That well, the whatever the anticyclonal flow looked like, it wasn't uh, blocking the westerly flow, bringing moisture off the obvious uh, water source out here in the Pacific, feeding our glaciers in the interior West. And so, again, I think you have to consider, well, what did the circulation really look like? And I have no expertise in this other than looking at maps. But here's one from 2004. It shows this monster anticyclone over basically the entire Laurentide, and what appears to be easterly flow off into Wyoming and Idaho, et cetera. But more recently, I found this model results by Jessica Conroy and colleagues that was done basically to evaluate Aeolian deposits and their paleo wind indicators there in the central and eastern U.S. But this looks a lot more like Peter's GCM model from back when. But again, I think bottom line is there's pretty good evidence that the anticyclone was not hindering development of glaciers from the LGM through the latest Pleistocene in the Rockies. And let's see, how are we for time? Ben, do you want to move on?
I think we've
Yep.
got about another 5 minutes.
Okay. Um, and that leaves time for questions.
That would include time for questions.
Okay, just very quickly, here's a paper we did way back when in Mount Taylor, or maybe not so way back when. Um, just it shows up on these old compilation maps like Porter Pearson Hamilton. There's a little spot here, but I always wondered, was there really ice up there? This is the most cirque-like feature on the Mount Taylor Massif, and so there's a really tentative paleoglacier reconstruction here with some field work that we did, busting the brush and thick timber, trying to find what might look like moraines. But ultimately, when LIDAR becomes available, um, maybe if somebody cares about this, wants to look at this more, I don't see clear glacial features here. It looks more like some kind of gooey mass movements that may be paraglacial in nature. And even a broader view, you can see a tongue of, some kind of uh, mass movement extending well down the valley here, past where we thought there might be possible moraines. Okay, and I think this thing here could be a lateral levee of a mass flow as opposed to a lateral moraine. Hard to tell. Okay, but I'm certainly not hanging my hat on any last glacial ice in that particular location. So that's a little detail. Just threw this in at the end in case anybody recognizes that particular Southeast Alaskan glacier, and hopefully we do have some time for questions.
Thank you, Grant. That was really, really great to see. And
Look,
I've meant to tell you before you started that Eric Leonard told me that he was very sad he couldn't join in person today. So I know he'll watch online and he'll appreciate the acknowledgement you gave him there. So questions for Grant? Please feel free to enter them in the chat or turn on your microphone.
Hey, I was going to make a comment about the upslope precipitation in the Sangres. Certainly the work we've done, we were initially very surprised that the ELAs were lower on the eastern side because, the expectation is we have moisture coming in from the west. And so we too were thinking upslope precipitation events, but there's some snow course studies that were done to suggest those upslope events are later than the peak in snow accumulation. And that led to the conclusion that a lot of the snow, and I think this is what you were alluding to, Grant, a lot of the snow is being transported from the western side or on those high plateaus over to the eastern side. And the specific reference is a guy named Gutman. And what he showed is that there was a lot of snow advection, which he distinguishes from deflation. So before the snow is deposited, it gets blown over to the eastern side, and that enhances the accumulation there.
Yeah, very interesting. Thank you for that, and I'll look for that reference. One thing, being at Montana State and Bozeman, that I was always impressed with, you could look up at the Bridger Range in the west side, and it's like a lot of bare rock, even in a good snow year. On the other side, on the east downwind side, that's where the great powder skiing is. And so, I mean, that's a quite local effect there, but it's very marked. And I think with dry snow in particular, um, that's a tendency. More questions?
All right. Well, thanks again, Grant. That was really,
Certainly.
really great to see. Sounds like you've had a lot of fun in your geomorphology classes over the years. So that was
It's been a really nice way to get students to really look in detail at contour maps, whether they're topographic or any other. We have people who, they can whip out a contour map in GIS in, 15 seconds, and then they don't know how to interpret it. So
right,
anyway,
right. Yeah, excellent stuff. All right. So, Jason, if you want to share your screen, hopefully that's an option for you here, and I'll introduce you while you're doing that. So our next speaker is Jason Briner at the University of Buffalo. He's a professor of earth sciences there. He holds a Bachelor of Science degree from the University of Washington, a master's from Utah State University, and a PhD from the University of Colorado. His studies on the history of ice sheets, glaciers, and sea level change have appeared in numerous journal articles. Jason's field research has taken him and his students above the Arctic Circle more than 40 times. He applies a broad toolkit of geological methods to reconstruct the climate and ice history in areas like Alaska, Norway, and Greenland, like we'll be hearing about today. He teaches introductory level courses on climate change, classes for geology majors on geomorphology, and upper level courses on glaciers and paleoclimate. And he's a fellow of the Geological Society of America. Glad to have you, Jason. Take it away.
Hi, everybody. First of all, can you hear me and see the screen?
Yep.
Full
yes,
screen? Well, I would, thanks very much. It's great to see everybody. Both a lot of friends in the audience and future friends if we haven't met. Also, I want to just extend an appreciation toward your patience in looking at a different topic today than you've seen before in this seminar. Not mountain glaciers in this talk, but I'm gonna take you to Greenland. There will be some kind of basic glacial geology though, so I think a lot of the methods and the expertise in this crowd is should have a lot of overlap. Um, so first of all, let's see if I can start. Okay, first of all, I have a question for everybody that you can put the answer in the chat. So what number is larger, do you think? The tallest living giraffe in the world or the height of sea level rise if you melted all of Greenland? I'm not seeing any responses.
I'm
I'll
going to
go with the
vote for the
giraffe.
giraffe.
You guys are going with giraffe?
Yeah.
Look at that. Okay. I happened to look up the world record living giraffe. And if anyone can squint, I don't know, Keith, how's your eyesight? It says,
Good. Sort of.
what, is, what does it say? 5.7 meters.
Correct.
Okay, so then who knows how much sea level comes out of the Greenland ice sheet if it all melts?
Less than a giraffe, more than a giraffe,
More, more than a
more than a
giraffe,
giraffe.
7.4 meters. So that giraffe would be drowned by, if it was standing on the beach, would be drowned by sea level if all of Greenland melted. So this is the world that I live in, and a lot of what drives a lot of my research, which is um, thinking about future sea level rise and how the Greenland ice sheet is part of that. What I'm showing here is a model simulation of Greenland in some distant future scenario, and it depicts how it is. I'm going to try to get that laser pointer thing. It depicts how it's smaller than today. So today is the black line, and this is some prediction of its future. But we also know from geologic evidence, which I want to walk you through, that in the middle Holocene thermal maximum, the Greenland ice sheet was also a reduced size smaller than it is today. Okay, so here's this really cool animation of this is not a model simulation. This is a series of GIS shape files of the Greenland ice sheet going from fat to skinny between the LGM in through the deglaciation into the Holocene. And this is a compilation by Leger et al. That came out last year, a couple years ago in 2024. And it pools together all the geochronology data that you all and I know and love, radiocarbon ages related to glacial deposits, all the exposure ages that have been published from around the perimeter of the Greenland ice sheet, um, tons of individual studies that map moraines and apply these various chronologies to those moraine limits, and then pools it all together to get an observation-based reconstruction, basically the state of the art, our knowledge pooled together about how the ice sheet may be changed through the Holocene. And here's that model or that animation again on the right, and on the left you see bar graph of the percent of Greenland deglaciated in all these various time slices. We're now into the Holocene, and we're looking at the demise of the Greenland ice sheet. And you can see that the record stops around 6,000 years ago, and now we're in a data gap. And that data gap exists because the Greenland ice sheet became smaller than its modern day footprint. And then sometime in the last 6,000 years, it got smaller, and then it grew back, obscuring all the glacial geologic evidence that we all like to work with. So we got to come up with other approaches to figure out what's going on with the ice sheet in this data gap, and we're trying to find ways to constrain that data gap more. Okay, so today I want to just do two brief vignettes of that address this data gap. I'm going to do a low budget version and then a high budget version. So the low budget version, using free access to Arctic DEM, much like the CalTopo LiDAR that we were all like drooling over. I don't know how much time you guys have all wasted looking at CalTopo, but I've wasted probably a year of my life so far. So we're going to look at Arctic DEM data. Okay, so I want to tell you about Ole Benneke. He's this Danish glacial geologist at the Geological Survey of Greenland and Denmark, GEUS. And here Ola has my former cat, RIP Crouton, on his lap. And I had the great benefit of working with Ola on a kind of a neat project, a low budget project. You didn't know if that you when you came to this, you'd have homework. This is your first homework assignment. Check out this paper. It's in the bulletin of the Geological Society of Denmark. It's a short little piece. This is our low budget work. So the study that this paper describes is in this northeast corner of Greenland. And in the northeast corner of Greenland, we have these huge ice streams coming out, the Northeast Greenland ice streams. And okay, so Ola appeared much earlier than more recent when he was with my cat. And he published a paper with Anker Weidick in 2001 from Northeast Greenland. And in that paper, that's been out for quite some time, as it's a broad paper, and they talk about a lot of cool glacial geology and relative sea level change in the northeast corner of Greenland. But in that paper, there's a small section that describes something called the Sandalen Moraine. And so recently in our group here in Buffalo, we've been working with a student who's drawing, here's another classic GIS experiment. He's drawing the outline of what's called on Greenland the historical moraine, but that's a little ice age moraine. He's drawing one line all the way entirely around the Greenland ice sheet. So we have like a polyline now product of the little ice age extent of the Greenland ice sheet. And when I was mapping up in this area, here's the historical moraine, that's the little ice age. But there's a very distinct trim line, you can see, especially right here where my cursor is, of another moraine that doesn't look like there's a vegetation trim line here. So that would be odd for there to be a vegetation trim line on like a really like a deglacial aged moraine like 8,000 or something like that. The other thing that Ola noticed when he was here is that they found shell fragments in this moraine. Now, this glacier, I'm going to go back a couple. This glacier, if it was gone, there would be sea level below the ice because the bottom of the glacier is below sea level. So when it retreats to a position smaller than today, the whole area floods and becomes ocean. So this glacier, when it was smaller than today and advanced back out to deposit the Sandalen moraine, it picked up seashells and incorporated those into the moraine like it would like a moraine boulder or an erratic boulder. So we have 6 shell fragments that Ola dated as part of that paper that date between 6,100 and 5,500, which means that this moraine post-dates that time period. Okay, so, oh yeah, here's my little cartoon about how that happens. So there's a fjord with mud with shells. Ice advances across the fjord, picks up that mud, puts it in its moraine. And if you go walking on that moraine today, this is what I did once in West Greenland. You can find all sorts of shells in these little ice age moraines where the glacier advanced through a fjord. Okay, so I was really curious about the Sandalen moraine, so I downloaded the Arctic DEM for free. And then I saw with my eyeballs a bunch of terraces here mapping that moraine, and it looked like there was some remnants of outwash terraces, and they came all the way up to the former position of the glacier when it deposited the Sandalen moraine. Maybe it's some kind of surge or something, not exactly sure. And here's a zoom up of what appeared in the paper. So some mapping of these terraces. This one I think is some kind of like outwash head. It comes right up to the moraine, and then there's this pretty cool flat outwash surface. Okay, so I wanted to know what the elevations of those terraces were, so I did an elevation transect of the south terraces and the north terraces, and here's the results. This is a topographic cross section. Here's the modern river, so this is like along this cross section line, and this is the modern fan delta, and then the ocean's out here at the A prime mark. So there's the moraine, here's these terraces, there's the outwash head. And if you just do like a super crude thing where you parallel the modern river, but when those terraces were formed, you can project those terrace elevations down to sea level to try to estimate what was the relative sea level when that glacier was depositing the Sandalen moraine and creating these outwash terraces. You can then bring over to the local relative sea level curve, which is this black line, the elevation of those terraces. I wrote Sandalen moraine here. They come over and they intercept the relative sea level curve between 4,000 and 5,000 years old, something like that. There's also, if you were looking really closely, I know I'm going fast, but if you were looking really closely, you saw on the bottom of this image, there's a raised marine delta at the current coastline that's 35 meters above sea level. That delta was formed when the Sandalen Glacier was further down the valley and its meltwater came down the side and then made that delta. At least that's my interpretation. And so if you think that that 35-meter ASL terrace is when the glacier was bigger, maybe when it was retreating after the being big during the last glacial maximum, this is the local marine limit in the area. That dates to about 7,000 if you pull out a chronology from this relative sea level curve. Oh, there's my fancy animation. And so just learned how to do that, by the way. So we think that the terrace and the moraine, the Sandalen moraine, dates to 4,600 plus or minus 400. That's this little intercept thing. And this means that the ice sheet here in Northeast Greenland was smallest between 7,000 and 4,600. So this is at least, it's not really knowing how far inland it went, but it's constraining the time period of Holocene minimum ice phase to this particular interval. Okay, that's the low budget part. And now I'm going to go to high budget. And when I talk about the high budget stuff, I can't do it without talking about Caleb. This is Caleb Walcott George. He's in the audience. He was a PhD student in my lab. He graduated last year. Now he's an assistant professor at the University of Kentucky. And this is basically Caleb's dissertation work. He's holding an ice core here. The goal of us going to Greenland was not to core ice, but I will show you later in a slide, we did get data from an ice core like this one. So that is a small part of the story. But I want to tell you about a paper of Caleb's that just came out this month, and this is the current issue of Nature Geoscience. So this is your second homework assignment, the second reading. Okay, the punchline conclusion from Caleb's work, which I'm going to talk you through briefly after this slide. But the punchline, in case it's not quite 5 o'clock here, but you might be thirsty pretty soon. The ice dome in this part of Greenland that I'll show you in the next slide was gone in the Middle Holocene warm period, and it began to grow back around 7,000 years ago, plus or minus 1,000. So I want to tell you how we got to that conclusion. This work is part of this program we've been running on Greenland. Well, it's now kind of over-ish, but we still have a lot of work to do to analyze all the material we got. It's called Green Drill. And this was an endeavor that we did in Buffalo along with Jörg Schaefer, who led the project out of Lamont. And then we had some other people involved as well. Sridhar from Penn State, Rob DeCanto from UMass, and quite a number of other people. Integral in getting this project done, here is a drill camp drilling through the ice so we can get samples from below the glacier and then ask those rocks down there, when was this ice over your head last gone? And we want to ask those rocks, interrogate those samples we collected with luminescence dating and also cause a whole suite of cosmogenic nuclides. And I want to talk just about Caleb's piece on the luminescence. The drilling couldn't have happened without our friends in the U.S. ice drilling program. Okay, here we are now, this time in Northwest Greenland. Before, my low budget study was in Northeast Greenland. In Northwest Greenland, we're going to go out to this little like thumb sticking out called Prudhoe Dome. We looked over every pixel of Greenland to figure out where we could use this drill and all of its requirements and restrictions and get a sample that would do some really meaningful science in a place that was technically possible to drill. And this was one of our selected drill sites, Prudhoe Dome. Here's a cross section of the dome. It's like a 500-meter thick dome resting on some rolling highland. And we drilled basically just off the tippy top summit, but basically in the summit area down to bedrock. This is our drill camp, by far the largest field logistics I've been involved with in my career. It was great fun. I probably aged 5 or 6 years because of all the stress involved. This is the drill that's called the ASIG drill. Everything was manually taken out of and put back in a DC-3 airplane. There was no forklift. All this stuff. Oh, so Caleb maybe aged a little bit. This came out of the plane, got set up on site, and this drill rig that you're seeing right here got us through 500 meters of ice, and then 509 meters of ice, and then 7.5 meters in the substrate below Prudhoe Dome. I want to point out Allie Balter Kennedy, who was a postdoc at Lamont, a PhD student, then a postdoc at Lamont. Now she's an assistant professor at Tufts. And Allie led a lot of the work of this core that we call the Prudhoe Dome core or the ASIG core. The ASIG was the drill that got us this core. This 7.5 meter long sub-ice core below 509 meters of ice consists of a bunch of sediments, mostly glacial till, and then we got the contact with the underlying bedrock. That's why it looks dark on the left and light on the right. The top is by Allie's face, and the bottom is way over here in the bottom right. So you read it like a book, up and down book, maybe a Chinese book. Okay, here's the sediment part. And what Allie has done is she's taken a very close look at some of these core sections. And here's this cool little fancy thing. We think it's like glacial till. And here's a CT scan of it, and you can see dense stuff. It's like a garnet gneiss kind of the local lithology, but there's other lithologies too, but that's a common one. And then there's ice lenses. These partings are ice lenses. And Allie worked with some permafrost folks at Fairbanks, and they think this is all permafrost. There's evidence that this is all permafrost stuff. Well, you can see up here in the corner OSL sample. So what Caleb did, Caleb worked with Nathan Brown, a professor at UT Arlington. And Nathan's a superstar in luminescence dating, and now Caleb is too. And so they work together. And here's the very simple cartoon of the core. They did single grain IRSL luminescence dating on sand size feldspar grains. And what they did is they measured the equivalent dose in the luminescence framework, 1, 2, 3, 4, 5, 6 different samples in a depth profile, okay, from the surface down to, well, maybe 85 centimeters, and then they skipped down and got a lower sample at like 175 centimeters, whatever that is. And then what you're seeing in this middle panel is the minimum age model. Okay, so in single grain, it's like for people who are familiar with exposure dating, well, you guys probably know how luminescence works. I don't. I learned a lot. But in exposure dating, if you dated 100 boulders on a moraine, some of them would tell you the answer, and then some of them would have inheritance. And so the minimum age model is just like some of those papers you've maybe seen in exposure dating where we're not going to look at the average of it all because that would bring in all the inheritance. We're just going to look at like the young mode, minimum age model. And these are just the minimum age, the minimum dose of the equivalent dose in the luminescence world. If you take the top 3 samples, pool them in this radial plot thing, which is basically like it's a way to look at data is like a histogram. This is like the bottom axis of a histogram. And then the way it spreads up from this bottom axis, which is the equivalent dose, it goes upwards, and then there's uncertainty. So this is basically like standard deviation. And so like if you can picture like a histogram, there may be like a young mode and then older modes. The different modes of the single grain luminescence data appear here as spokes, like spokes on a bicycle wheel, which Keith can relate to. And the lowest spoke here on the low DE, so that's 100 and that's 0. What is that, Caleb? 80, 60, 40, 20, something down here. So really low spoke. That's an interpretable mode of these data, and that mode has an equivalent age of 7,000. So, okay, now what to do with this number 7,000? Well, because there's permafrost in the area, remember the permafrost? And because it's a depth profile, it's kind of like youngest at the top. And in fact, I was looking at this, almost this entire spoke is made up of just the uppermost sample, but there's also inheritance, or what do you call it in luminescence? Impartial bleaching or not full bleaching. So there's some not fully bleached grains, but then there's some here that are. So because there's a bit of a depth profile here and there's permafrost, this is the conceptual model that Caleb came up with. So here's ice. There's a bunch of grains. Each one of these grains has a luminescence signal. Once ice has been there a long time, that signal builds up in those grains. When you get an ice off episode and the sunlight beating down on the ground, it's going to be restarting the luminescence clock. But we also have permafrost mixing around the grains. So it's bringing some of the completely bleached grains down and mixing it down into the sediment column. At the same time, it's mixing incompletely bleached grains upward and kind of mixing it all together in like an active layer in the permafrost profile. That process then instantly stops and becomes locked and frozen when ice, cold-based ice, regrows over the ground. So then you lock in, there's no more motion of these grains, there's no more resetting from the sun, and then the clock starts. And then here we are today, with our green drill project, grabbing those samples, and what maybe was bleached is now has 7,000 years of equivalent buildup of the luminescence signal. So what that means is that the 7,000 year age we got isn't an age of exposure per se, or it's an or not an sorry, it's not an age of sediment deposition like it commonly is in luminescence applications. It's recording when the ice came over the site and shut down the permafrost processes. The other thing that can, okay, so what that means is the Prudhoe was gone in the Holocene. It did not survive the Holocene. It went away and then regrew back in the Neoglacial. One other piece of evidence confirms that, and this goes back to Caleb's ice core that he was holding. We measured the O18 in Prudhoe Dome. Here's Camp Century for scale, which is another ice core up there, which goes so deep it taps into last glacial maximum. And in the O18 world, when you get into LGM ice in an ice core, you get super depleted values. We never got super depleted values in Prudhoe Dome. It suggests that the entire ice column on top of the rock is Holocene in age. And the dome, another piece of evidence that says that the dome didn't survive the Holocene. And that's my like speed talk through those two case studies. I'm done. Thank you. And if I'll take questions.
Awesome. Thank you, Jason. Questions?
I have one, Ben.
Go ahead, Cal.
Hey, Jason, nice talk. And Grant, too. Thanks for your time. It was neat to see. I, too, studied under Bill Locke and Ken Pierce. And Jason, is anybody still doing any work on the MIS 1211 record in Greenland? I got inklings and some gossip that there was an interval, between 350 and 450,000 years where the ice sheet completely uh, dwindled away, and there's actually oxidized soils down below it, indicating semi-arid environments.
Yeah, it that's a burning question about when the last time Greenland got really small. Um, the candidate time periods that people tend to be looking at are the last interglacial, stage 5e, 125,000 years ago, and another biggie that people are looking at is stage 11, marine isotope stage 11, which is quite long interglacial from about 400 to 430,000 years ago. And the most recent work on that interval probably comes from Camp Century, this very core that I just showed you with those O18 values. That was collected in the 1960s, by the way. And
Wow.
that ice core it was the first time anyone in the world drilled from the surface of the ice down to bedrock. Um, that was done in part by Chet Langway, who actually was in my department for a chunk of his career after he was at Krell. Um, and anyway, when they in the 60s, they got into the bed, and that's what Paul Bierman and a bunch of people have been working on is the sediments from the 1960s that they sort of rediscovered in the Copenhagen freezer 6 or 7 years ago. And Tammy Rittenauer has luminescence dated those basal sediments to 400,000 and change.
Hey,
So,
so I should talk to Tammy.
yeah, so they think that Camp Century was ice free during stage 11, but it's one dot in Greenland. We don't really know how
Yeah.
much of the ice sheet got burned off in that interval. We need more of these kinds of studies of what they did at Camp Century and what this little green drill thing. Of course, green drill we're just doing around the fringes, but there's the technology exists to go get samples and we have the toolkits available to analyze it to answer these questions, and we're just kind of everyone feels like we're just getting started, but it's expensive.
Yeah, I'm sure it's extremely expensive. No, I've been doing a little bit of collaboration with a guy named Candy out of the UK, Ian Candy. Um, and just in the work he's been doing on MIS 11, 12 in Europe, and comparing that with what I've been doing from Kansas to New Mexico in that interval.
Okay.
Just
Yeah.
trying to see. And I'd heard these rumors about the Greenland. Maybe Tammy had mentioned something, but just curious because you're steeped in that community. Um, but yeah, nice talk. It's crazy things dwindle away and are growing back in this day and age, you know.
Yeah, totally.
Thanks again.
Yeah. Yeah,
Good to
yeah.
see you.
Thanks for the question.
Yeah, good to see you.
Yeah, you too. Joe.
Um, yeah, first of all, great talks, both of them. Thank you, Grant, and thank you, Jason. And I have a question for you, Jason, that's sort of back to your low budget part of your talk. Those shells that Ola found and dated, are there any concerns with reservoir age corrections that might change the story that you told us? Or is that a concern up there, or is it pretty well known?
Yeah, I think when it comes to reservoir correcting shells, Carly was on the thing earlier. Is she there? She might have something to say about that. She's been thinking about a lot of that in Greenland lately.
Hmm.
You mean the marine reservoir correction for the
Yeah,
shells? Yeah, I
they were
mean, I
marine,
think
right?
what's that?
They were marine, right?
Yeah, exactly. Yeah, those are marine shells. And
Yeah.
I think probably for that paper, I just applied whatever uh, local delta R value is that people apply in that part of the world. Um, what is it, Carly? It's like it's the global value plus like 50 years or something.
Yeah, that's what they suggest to do from like modern shell dating. They get around -50, I think, from the Marine 20, which is 550. And then we are have done a couple calculations on terrestrial marine pairs a little bit south of where Jason's working, and find that the relationship looks good back to like maybe 8,000 years. And then before that, we find that there might be a bigger reservoir correction. So I think the shells that he's working on are probably within that range of that -50 value.
Okay, so pretty well constrained then.
Yeah, I think as far as people's best guess, I mean,
Sure.
you know, it's a really good question. To be completely honest, that study, I think there's a lot of wiggle room in just how we did that. Um, I think there's probably some larger uncertainties in there depending on those correlations and extrapolations of those surfaces down to sea level and all that, that my guess would probably result in like a larger error of the whole study than like something like the reservoir correction uncertainty.
Yeah, sure.
But
Great. Thank you.
yeah, it'd
Yeah.
be great to go back there and get more shells because the more you date, the more you might fill in the range of time that the ice was smaller than present.
Yeah, sure.
But then it would be not low budget anymore.
All right, great. Any more questions for Jason? Thanks everyone for sticking around. I promise I'll figure out Zoom before our next meeting here. All right. Excellent. Well, Jason, I really appreciate you staying on a little bit later. Again, I apologize for the late start. Grant, great to hear from you. This was a great way to begin our 5 week long series here. Next week will be on Thursday. Same time, just going on Thursday to accommodate folks who can't make it on Fridays. So I'll send an announcement on that one. We're going to hear about glaciation on Mars, which will be pretty cool. So thanks again, everybody. We'll see you in just under a week.